A new kind of vision is letting us see through the world's most solid walls. This is the power of muon imaging, a revolutionary technology that is fundamentally changing how we explore history's greatest monuments. By the end of this journey, you will understand how particles from distant stars are revealing secrets that have been locked in stone for thousands of years. What colossal void was recently confirmed deep within the Great Pyramid, and why does its purpose remain a profound mystery? How could the same tool that scans a pyramid also predict a volcanic eruption? The answers lie in a silent rain of cosmic messengers that pass through us every second. What forgotten room do you believe is still waiting to be found? That silent rain of cosmic messengers is not just a metaphor. It is a physical reality, a downpour of fundamental particles called muons. To grasp how they reveal hidden chambers, we need to understand where they come from and what makes them so extraordinary. Their story begins not on Earth, but in the violent hearts of dying stars far across the galaxy. When a massive star explodes as a supernova, it blasts out protons and atomic nuclei at nearly the speed of light. We call these cosmic rays. After traveling for millions of years across interstellar space, some of these rays finally reach our planet. They slam into the molecules in our upper atmosphere, and in that colossal collision, new particles are born. Among them are muons. Think of a muon as a heavy cousin of the electron, but where an electron would be stopped by a sheet of paper or a thin layer of metal, a muon is staggeringly powerful. It is born with such immense energy that it can penetrate solid matter with ease, passing through hundreds of meters of stone before it finally decays into other particles. This is the crucial difference between muon imaging and the X-rays you might get at a doctor's office. An X-ray machine generates radiation to see through soft tissue, but it is stopped by dense bone. Muons are the opposite. They are natural, they arrive for free from the sky, and their great challenge is not penetrating bone, but penetrating a mountain. They are so penetrating that they pass through you right now, several hundred every second without you ever noticing. This constant, invisible shower gives us a perfect natural probe. The core principle is beautifully simple. As muons rain down through an object like a pyramid or a volcano, the denser the material, the more muons it absorbs. Solid rock will block many muons. An open space, a hidden chamber, or a lava tube will block far fewer. So if you place a sensitive detector inside or beneath a large structure and count the muons arriving from different angles over weeks or months, you begin to build a picture. Areas where you detect more muons than expected are, in essence, shadows. They are the signatures of voids. The monument itself becomes a filter, and the muon flux is the developing solution that brings its hidden image to light. Understanding this cosmic messenger transforms it from a particle of physics into a key, one that is patiently unlocking doors we never knew were there. This key had to wait for the right door to be found. The first person to truly grasp its potential was not an archaeologist, but a physicist named E.P. George. In the 1950s, George conducted a simple, brilliant experiment. He placed a muon detector inside a railway tunnel in Australia. His goal was not to find a hidden room, but to measure something far more fundamental: the thickness of the rock overhead. By counting how many muons made it through the mountain, he could calculate the mass of material above him. It worked perfectly, and in that moment, a new field of vision was born. Yet for years, this remained a tool for geologists and engineers, a clever way to peer into mountains or check the density of materials. Its leap into archaeology was sparked by one of the 20th century's most inventive minds, Luis Alvarez. Alvarez, a Nobel Prize-winning physicist, was captivated by the pyramids. He wondered if the same technique could settle a long-standing question. Were there still undiscovered chambers within the Pyramid of Khafre, the second Great Pyramid at Giza? In the 1960s, he and his team placed a series of muon detectors in a chamber deep inside the pyramid, known as Belzoni's tomb. For months, they patiently recorded the silent rain of particles passing through the stone above them. The results were definitive and, in a way, disappointing. They found no evidence of large, hidden rooms, but Alvarez's experiment was a monumental success for a different reason. He had proven beyond any doubt that muon imaging could be used to scan the heart of an ancient monument. He published his findings with a confident title, Search for Hidden Chambers in the Pyramids. The search had come up empty, but the map for all future searches had been drawn. For decades after, the technology continued to evolve in other fields. It became a vital method for monitoring the contents of nuclear reactors, offering a way to see inside sealed containers of spent fuel without ever opening them. It was used to study the internal structures of volcanoes, providing clues about magma movement that could warn of eruptions. The detectors became smaller, more sensitive, and vastly more capable. Yet the dream Alvarez ignited of revealing history's greatest secrets never faded. It simply needed the right project, the right monument, and a new generation of scientists ready to look. The tool forged in particle physics labs and nuclear facilities was about to find its most poetic application, not in monitoring the power of the atom, but in rediscovering the ambition of the pharaohs. The stage was set for a return to Giza, but this time the target was the grandest pyramid of all. The leap from Luis Alvarez's pioneering experiment to today's discoveries required a revolution in the tools of the trade. Modern muon imaging is not a single magic box, but a sophisticated technological orchestra, with different types of detectors playing different parts to create a complete picture. To understand the stunning images we now see, we need to meet the key instruments in this cosmic symphony. First are scintillator detectors. These use special plastic or crystal materials that have a fascinating property. When a muon passes through them, the material emits a tiny, instantaneous flash of light. Sensitive photodetectors, much like ultra-powerful digital camera sensors, capture that flash. Each flash is a digital whisper saying a muon was here, and by arranging grids of these scintillators, scientists can track not just that a particle came through, but the precise angle of its path. Then there are gas-based detectors such as drift tubes. Picture a long, sealed metal tube filled with a specific gas. When a muon zips through this gas, it ionizes it, knocking electrons loose. A high-voltage wire runs down the center of the tube, pulling those electrons toward it. By measuring the tiny time it takes for the electrons to drift to the wire, researchers can pinpoint exactly where the muon passed through. It is a stopwatch for a particle, translating time into spatial coordinates with incredible accuracy. Finally, there is a beautifully analog technology, nuclear emulsion films. These are special layers of gelatin infused with silver bromide, acting much like a very, very slow photographic film. When a charged particle like a muon travels through the emulsion, it leaves a latent track, a microscopic trail of damage. After weeks or months of exposure inside a pyramid, the films are carefully developed. Under a microscope, the trails appear as fine lines, a permanent record of every muon's journey. It is a direct physical snapshot of the invisible rain. So how do these tools turn into a three-dimensional map? The process is a masterclass in patient observation and digital reconstruction. Teams will strategically place arrays of these detectors inside known chambers of a monument or in tunnels dug beneath it. For months, they sit in silence, counting. Each muon that passes through is logged, its angle of arrival and energy recorded. Over time, millions of these trajectories are gathered. Think of it this way: if the monument were a loaf of bread and the muons were countless tiny needles being shot through it, the detectors on the other side would record which needles made it through and where they came from. Needles that passed through a dense knot in the bread, a section of solid stone, would be blocked. Needles that passed through an air bubble, a hidden void, would sail through unimpeded. By compiling the directions of all the muons that did get through, a computer can work backwards. It calculates which paths were more open, painting a shadow image of the structure's density. Areas with higher muon counts appear as bright spots on the map, signaling less material, while dark areas show where the stone is thick and solid. This painstaking analysis transforms an abstract torrent of particle data into something we can visually comprehend, a ghostly, three-dimensional blueprint of the unseen. The stone itself becomes transparent, not to our eyes, but to the relentless logic of physics. With this powerful toolkit now assembled, the stage was finally set for its most ambitious application, a project that would scan the last of the ancient world's 7 wonders. The grandest test for this new vision arrived in 2017 with an international mission named ScanPyramids. Teams from Japan, France, and Egypt brought their most advanced muon detectors to Giza, not to scan from a distance, but to place them deep within the pyramid's belly. Their primary listening posts were the Queen's Chamber and the corridors that snake around it, spaces known for millennia but now repurposed as high-tech observation decks. For months, in the cool, still air of the ancient interior, the detectors sat in silence. They were not searching for treasure, but for absence, for the subtle signature of empty space within millions of tons of limestone. The anticipation among the researchers was a palpable tension, a mix of scientific rigor and the sheer wonder of potentially rewriting what we knew about a 4,500-year-old structure. Then the data began to speak. The muon counts told a clear and astonishing story. High above the Grand Gallery, that magnificent ascending corridor that leads to the King's Chamber, the particles were flowing through in significantly greater numbers. The map took shape, revealing a colossal hidden space. The team named it the Big Void, an immense chamber nearly 100 feet long, with a cross-section similar to the Grand Gallery itself, sitting like a hidden twin in the heart of the monument. Its discovery was a watershed moment, the definitive proof that muon imaging could reveal major, unknown architectural features in the world's most studied building. But with revelation came deeper mystery. What was this void for? The leading theory suggests it could be a structural relieving chamber, designed to redistribute the immense weight of the pyramid's upper layers away from the Grand Gallery below, a masterpiece of ancient engineering foresight. Yet its precise design and whether it served a ceremonial purpose remains entirely unknown. No corridors lead to it, no shafts point toward it. It is a sealed space, a secret held perfectly by the stone for 45 centuries, now hinted at by particles from the cosmos. This was not just a new room found, it was a fundamental change in our relationship with the past. It proved that our greatest monuments are not closed books, but texts we are only now learning to read in a new light. If this could be hidden in the Great Pyramid, what other architectural secrets are waiting patiently for their own silent rain of particles to reveal them? The quest for hidden chambers was not confined to the sands of Egypt. Across the world, in the vast ancient city of Teotihuacán, Mexico, another monumental pyramid stood as a perfect subject for this new cosmic eye. The Pyramid of the Sun, a colossal stepped structure built by a mysterious civilization centuries before the Aztecs, held its own secrets. Unlike the stone labyrinths of Giza, this pyramid was constructed from millions of sun-baked mud bricks and rubble, then faced with stone. The central question here was different. While Egyptian researchers often searched for specific hidden rooms, the team from the National Autonomous University of Mexico and the University of Texas had a broader goal. They wanted to peer into the very heart of the pyramid's construction, to understand its density and internal makeup, and to search for any signs of internal chambers that might hold clues about the city's lost rulers. To do this, they placed their muon detectors not inside the pyramid, but deep within a natural tunnel that runs beneath it. For months, the instruments listened to the cosmic rain passing downward through 250 feet of ancient fill. The results were both definitive and illuminating in a different way. The Muon Map revealed no large, empty chambers akin to the Big Void in Giza. Instead, it painted a detailed picture of the pyramid's internal composition. The data showed areas of varying density, likely corresponding to different construction phases or the use of different materials in its core. This was a revelation of a different kind. It proved that muography is not merely a tool for finding spectacular emptiness, but for creating a detailed internal blueprint. It allows archaeologists to see the construction phases, to identify where builders might have used looser fill or more compact materials, all without disturbing a single brick. This contrast between the two pyramids highlights the technology's adaptability. In Egypt, the search was for precise, architecturally designed voids within a near-solid stone mass. In Mexico, the probe revealed the heterogeneous heart of an earthen giant, built in layers over time. One application hunts for hidden rooms, the other reconstructs the very process of building. Both approaches offer a profound shift in methodology. For generations, understanding a pyramid's interior meant either relying on external surveys or invasive digging, which risks damaging the structure. Muon imaging offers a third way, a form of cosmic archaeology that respects the integrity of the monument while revealing its deepest truths. It transforms these silent monuments from impenetrable mysteries into open books, their pages written in the language of density and void, patiently read by particles from the stars. If we can see the density of a pyramid's core, what other forgotten engineering choices of the ancient world are waiting to be decoded? The same cosmic messengers that map ancient tombs are also standing guard over some of Earth's most powerful natural forces. To truly appreciate the versatility of muon imaging, we must look beyond the silent pyramids to the rumbling mountains where the planet itself is being reshaped. This is the story of Muon Volcanology, a field where the particles become silent sentinels, monitoring the deadly plumbing beneath volcanoes like Mount Vesuvius in Italy and the Soufriere Hills in Montserrat. Here, the goal is not to find a hidden chamber, but to locate something far more dynamic and dangerous: the rising columns of molten rock known as magma conduits. Scientists place their muon detectors strategically on the slopes of these sleeping giants. Just as a void in a pyramid allows more muons to pass through, so too does a conduit filled with less dense, bubbling magma compared to the solid rock around it. By creating a detailed density map of the volcano's interior over time, researchers can watch these channels evolve. They can see magma begin to pool and ascend, offering a potential early warning sign, a glimpse into the mountain's intentions weeks or even months before the ground shakes or gas emissions spike. This application draws a powerful parallel. Muon imaging reveals the hidden architecture within human-made mountains of stone, and it reveals the shifting architecture within natural mountains of fire. Both are stories written in density and void. The success in volcanology is not just a fascinating side note, it is a critical reinforcement of the technology's robustness. It proves that muon imaging works in wildly different environments, from the dry, static mass of a pyramid to the hot, pressurized, and ever-changing interior of a volcano. This cross-disciplinary triumph highlights a deeper, unifying principle. Whether you are interpreting the data from Giza or from Vesuvius, you are fundamentally reading the same language, the language of fluid dynamics in rock. In a volcano, the fluid is molten lava moving through solid conduits. In an archaeological site, the fluid might be groundwater that has seeped into cracks over centuries, or even air filling a forgotten chamber. The Muon Map shows you where the material is less dense, and your scientific context tells you what that likely means. Understanding how to distinguish the signature of a magma tube from that of a water-filled fissure or an architectural void is where the real detective work begins. It is this interpretive layer built on geology, physics, and history that transforms a shadow on a detector into a discovery. So the next time you see an image of a hidden void in a pyramid, remember that the same cosmic rain is also helping scientists listen to the heartbeat of the Earth itself, protecting communities by forecasting fury through the silent passage of particles from space. This cosmic detective work soon turned toward another Egyptian enigma, one with a famously peculiar silhouette. The bent pyramid at Dosha stands apart from its neighbors, its smooth sides abruptly changing angle halfway up, giving it a distinctive, almost stumbling profile. This architectural shift, a correction made by the builders over 4,500 years ago, has fueled a persistent theory among Egyptologists. Many believe this pyramid, built for Pharaoh Sneferu, might hold undiscovered internal spaces, perhaps even a hidden upper chamber that corresponds to its altered design. To test this, a team from Nagoya University and Japan's High-Energy Accelerator Research Organization, known as KEK, embarked on a mission. Their goal was to use muons to see if the stone held secrets that eyes and conventional tools could not perceive. The work itself was an exercise in patience and precision. In 2016, the researchers carefully installed their muon detectors inside the pyramid's accessible lower chamber. This was not a spacious laboratory but a confined, ancient room where every cable and sensor had to be placed with immense care to avoid disturbing the historic site. The air was still and thick with the dust of millennia. For months, the instruments silently counted particles, gathering data from the massive stone mass above and around them. The core hypothesis was direct. Could the muon flux reveal a density anomaly, a shadow of emptiness behind the northern wall of that chamber, possibly leading to a corridor or room that had been sealed since the pyramid's construction? When the data was finally processed, it offered a tantalizing yet incomplete picture. The muon counts did suggest a region of lower density, a potential void located behind the north wall. This was not a crisp, clear image of a chamber, but more of a statistical hint, a whisper from the stone. In the world of muography, such results are common and incredibly important. They rarely provide a finished map. Instead, they offer a compelling clue, a reason to look closer, to ask new questions, and to plan the next, more targeted scan. The findings from the bent pyramid did not end the mystery, they reframed it. They initiated a fresh cycle of scholarly debate, bringing Egyptologists and physicists together to interpret what that subtle signal might mean. Was it a small construction gap, a forgotten storage niche, or the entrance to something more significant? The answer remains hidden, but now there is a scientific trail to follow. This is the true rhythm of discovery with this technology, each scan peeling back a layer of uncertainty, not to provide a final answer, but to guide the next, more informed question. If a mere hint from the bent pyramid can stir such intrigue, what might a definitive signal reveal in another of the world's sealed monuments? A muon map is a whisper, not a shout. It presents us with a landscape of shadows and probabilities, a grainy image where brighter spots suggest less material. But turning that suggestive glow into a confident statement, like "here lies a pharaoh's forgotten chamber," is where the real scientific challenge begins. Every anomaly on the map is a question. Is this bright patch the clear outline of a built room with flat walls and a purpose? Or is it the ragged signature of a natural crack, a place where the bedrock split millennia ago? Could it simply be a section where the ancient builders, perhaps in a hurry, used looser rubble as fill, creating a zone of lower density that mimics a void? And sometimes the signal itself might be a trick of statistics, a random clustering of data points that looks meaningful but is ultimately just noise. This ambiguity is the frontier of muon archaeology. The particles reveal a possibility, but they rarely declare a function. To answer that, researchers must become cosmic detectives, cross-referencing the muon data with every other clue they can gather. They deploy ground-penetrating radar, which sends radio waves into the stone to reflect off boundaries between materials. They use thermal imaging cameras to measure slight temperature differences on the pyramid's surface at different times of day, as hidden voids can retain heat differently than solid rock. Most importantly, they consult the blueprint of history itself, the known architectural principles of the civilization that built the structure. They ask, does the size, shape, and alignment of this potential void make sense within their building techniques and cultural practices? This collaborative interpretation is beautifully illustrated by the ongoing story of the Big Void in the Great Pyramid. Its initial discovery in 2017 was monumental, but the image was coarse. In 2023, an international team published a new analysis using additional data from different detector placements and more sophisticated reconstruction algorithms. They refined the void's estimated dimensions and suggested its shape might be more corridor-like, possibly even sloping, paralleling the grand gallery beneath it. This wasn't a correction of the first finding, but an evolution. Each new dataset and each new perspective sharpens the picture, moving from a blurry suggestion of a space to a clearer, though still mysterious, architectural feature. This process underscores a vital truth. Muography is not a magic eye that sees all answers. It is the most powerful listening device ever devised for stone, but it is part of a larger orchestra of discovery. The cosmic particles provide the lead melody, the fundamental signal of something hidden. Ground-penetrating radar adds harmony, thermal imaging offers rhythm, and historical context provides the essential lyrics. Only when all these instruments play together can we begin to understand the full song the past is trying to sing. So the next time you hear of a hidden chamber found by muons, remember the quiet, meticulous work that happens after the initial announcement, the slow and careful translation of a statistical ghost into a chapter of human history. This silent listening offers a profound shift in how we approach the past. For centuries, the only way to know what lay inside a sealed tomb or beneath a temple floor was to physically break through, to drill, to dig, to dismantle. These methods, while sometimes necessary, carry inherent risks. A core drill might miss a hidden chamber by inches or inadvertently damage a fragile mural. Excavation, even when meticulously planned, is an irreversible act. Once soil is removed and context is disturbed, it can never be perfectly replaced. Muon imaging presents a different path, one guided by a non-invasive ethos. The detectors do not send out any energy or radiation of their own. They simply receive the natural cosmic particles that have been falling for eons. This passivity is their greatest strength. It means they can be placed in a chamber containing 4,000-year-old pigments without risking the slightest fade, or near delicate organic materials without causing any chemical change. The monument experiences nothing but the presence of a silent, unassuming instrument. This aligns perfectly with the core principle of modern conservation: first, do no harm. The goal is to understand and preserve heritage, not to win a race for discovery at any cost. Consider a fragile site like an ancient burial complex where the structural integrity is uncertain. Sending in a team with drills could trigger a collapse, destroying the very history you hope to save. But placing muon detectors around or beneath such a site poses no structural risk. They gathered data for months, building a map that can then guide any future, minimally intrusive examination with surgical precision. This technology also opens doors to culturally sensitive locations. There are sites around the world where traditional excavation may not be permitted out of deep respect for the beliefs of descendant communities or the sanctity of the location. Muography offers a respectful alternative, a way to learn about the site's construction and layout without disturbing its physical or spiritual integrity. It allows for a conversation between science and cultural preservation, where new knowledge does not demand a sacrifice. This principle is what elevates muon imaging from a mere tool to a new philosophy of exploration. It acknowledges that our curiosity about the past must be balanced with a duty to protect its legacy for future generations. We are no longer just treasure hunters or puzzle solvers, we are stewards. And the most powerful tool a steward can have is one that reveals secrets without leaving a single mark. This philosophy of stewardship finds perhaps its most urgent application not in a desert, but beneath a living city. The ancient volcanic rock beneath Naples, Italy, holds a labyrinthine history. Here, the Greek and Roman builders who founded the city did not just construct upward, they carved downward, creating vast aquifers, storage chambers, and networks of tunnels in the soft, tough stone. Over centuries, these subterranean spaces were expanded, forgotten, and sometimes rediscovered, creating a fragile honeycomb beneath the modern metropolis. This presents a dual challenge. How do you protect the priceless archaeology hidden below while ensuring the safety of the people and buildings above? The Muon project in Naples provides a stunning answer, deploying muon detectors as permanent sentinels in this underground world. Unlike the temporary scans in Egypt or Mexico, here the detectors are installed for long-term monitoring. They act like cosmic X-ray machines running continuously, building a living, three-dimensional map of the subsurface density. The primary goal is civil protection. By tracking changes in the muon flux over time, scientists can detect subtle shifts in the rock, signs of new voids forming or existing ones expanding, which could warn of potential sinkholes or structural instability long before the street above shows any sign of distress. But while they monitor for modern hazards, these same particles are also performing a constant archaeological survey. The tough rock presents a perfect puzzle for muon imaging. A naturally formed air pocket, a 2,000-year-old Roman water cistern, and a burial chamber from a later era will all appear as voids on the Muon Map. The raw data alone cannot tell them apart. This is where the interpretive skill of the researchers becomes an art form. They must cross-reference the muon shadows with historical maps, ground-penetrating radar scans, and the known construction techniques of different eras. The signature of a man-made tunnel, often straight and with regular dimensions, begins to stand out from the irregular, organic shape of a natural cave. The outline of a carefully carved burial niche distinguishes itself from the rough-hewn wall of an ancient quarry. In this way, the technology does more than find empty space. It begins to categorize the emptiness, separating geological history from human history. This case study beautifully expands what we mean by monumental architecture. It is no longer just about pyramids and temples standing in isolation. It is about the entire hidden foundation of a city, a layered masterpiece of engineering and adaptation carved directly into the earth itself. The muons here perform a dual service. They are both guardians of the present, watching for instability that could threaten lives, and archivists of the past, slowly revealing the forgotten blueprints of the ancient city beneath the city. This seamless integration of safety and discovery shows a future where our deepest history and our daily security are protected by the same silent rain from the stars. The true power of muon imaging is revealed not in isolation but in collaboration. It is the lead instrument in a technological orchestra, where each tool plays a distinct part to compose a complete diagnostic symphony. Alone, a muon map provides a powerful but grainy suggestion of what lies within. Combined with other non-invasive eyes, that suggestion crystallizes into a high-definition portrait of the past. This synergy transforms intriguing shadows into confident discoveries. The process often begins with a bird's-eye view using LiDAR or light detection and ranging. Mounted on aircraft or drones, LiDAR scanners fire millions of laser pulses at a monument's surface. By measuring the time it takes for each pulse to bounce back, they construct a staggeringly precise three-dimensional model of every external contour, every crack, and every subtle indentation. This digital twin becomes the essential canvas, the exact frame upon which all internal data will be painted. With the exterior perfectly mapped, the next tool looks for whispers of the interior on the surface itself. This is infrared thermography. As the sun heats the stone of a pyramid or a fortress wall throughout the day, that heat slowly soaks inward, but a hidden void beneath the surface acts as an insulator. The stone directly above a hollow space will heat up and cool down at a slightly different rate than solid stone. An infrared camera, sensitive to these minute temperature differences, can detect these thermal shadows. A warm patch at dawn or a cool patch at dusk might trace the outline of something hidden below, offering a crucial surface clue that guides where to look deeper. Then comes the sound of the structure. Seismic refraction surveys send gentle vibrations into the ground, often with a simple hammer strike on a metal plate. Arrays of geophones listen for the echoes, just as sound travels differently through air, water, and solid rock. These seismic waves change speed as they pass through materials of different density and elasticity. The data creates a map of the subsurface's mechanical properties, showing where the ground is firm and consolidated versus where it might be fractured or hollow. Now imagine a hypothetical workflow at a mysterious mound, a potential burial site, or a ruined temple platform. The initial broad scan comes from muon detectors placed around its base. After months of counting, the resulting density map shows a prominent, intriguing region of lower density deep within the mound's core. It is a bright spot, a candidate void. But is it a single chamber, a network of tunnels, or just a zone of loose rubble? The thermal imaging team is directed to that specific area. Their cameras, scanning at different times of day, might reveal a faint thermal anomaly on the surface exactly above the muon signal, strengthening the case for a deliberate void. Next, a targeted seismic survey is conducted over that precise zone. The vibration data could indicate that the material there is not just less dense, but also has different elastic properties, consistent with an open space rather than simple fill. Finally, ground-penetrating radar units are brought in for a close-up examination. GPR sends radio waves into the ground, and their reflections can outline interfaces with stunning clarity. Focused solely on the area flagged by the other three methods, the GPR might reveal the sharp, angular reflections of man-made walls or a flat ceiling, confirming the architecture of a room. This layered approach is the future of exploration. Muons provide the deep, penetrating overview that says, "Look here." The other techniques zoom in, each adding a layer of context, texture, and certainty. Together, they build a composite, three-dimensional model of the hidden interior with minimal guesswork and absolutely no disturbance to the site. It is a conversation between technologies where cosmic particles, light, sound, and radio waves all contribute their unique testimony, allowing us to listen to the past with unprecedented clarity. Behind every headline announcing a hidden chamber lies a monumental effort of its own. A muon detection campaign is far more than placing a high-tech box inside a pyramid. It is a complex scientific expedition that unfolds over years, not days. The journey begins long before any detector sees the inside of an ancient tomb, with the painstaking construction and calibration of the instruments themselves. These are not off-the-shelf devices. A muon detector for archaeology is often a custom-built array of scintillators or drift tubes, engineered for sensitivity and durability. The materials are specialized, the electronics are precision-tuned, and every component must be calibrated against known sources to ensure its readings are accurate. Building just one of these systems can cost hundreds of thousands of dollars, a significant investment that requires dedicated funding. This leads to the crucial question of support. Major projects like ScanPyramids are not funded by a single entity, but through intricate international partnerships, grants from scientific research councils, contributions from universities, and sometimes collaborations with private institutions pool the necessary resources. It is a global effort in pursuit of a shared human heritage, where a physicist from Japan, an engineer from France, and an archaeologist from Egypt all bring their expertise to the same table. Once the equipment is ready, the real-world challenges begin. Gaining permission to install instruments inside a protected World Heritage Site is a diplomatic and logistical feat involving governments, ministries of antiquities, and local experts. Then comes the deployment. You cannot simply plug a detector into a wall socket in the heart of the Great Pyramid. Teams must run heavy-duty power cables from distant generators or install solar arrays, all while ensuring not a single cable or bracket damages the ancient stone. The detectors themselves need a stable, controlled environment, protected from dust, humidity, and the inevitable temperature swings within a massive stone structure. In remote locations, this means building protective housings and establishing a secure, long-term presence, often with team members taking shifts to monitor the equipment. And then you wait. This is the most patient phase of all. To gather enough muon tracks to form a statistically significant image, the detectors must listen for months, sometimes over a year. The particles arrive in a random, silent drizzle, and building a clear picture from that drizzle requires an immense volume of data. There are no instant results, only the gradual accumulation of cosmic whispers. This lengthy timeline underscores the collaborative expertise at the core of every project. A successful campaign is a conversation between disciplines. The particle physicists design and operate the detectors, processing the raw data into density maps. The archaeologists and Egyptologists provide the essential context, interpreting those maps by asking, does this shape align with known burial practices or construction methods from this dynasty? The engineers solve the practical problems of installation and power in extreme environments, and project managers coordinate it all, balancing budgets, timelines, and the delicate protocols of working at a historic site. Understanding this immense behind-the-scenes effort reframes what a muon discovery truly represents. It is not the flick of a switch that reveals a secret, but the culmination of years of funding proposals, engineering ingenuity, diplomatic coordination, and scholarly debate. Each new void announced is a testament to human perseverance, a modern expedition that mirrors the ambition of the ancient builders themselves. With such profound effort required to see inside our greatest monuments, where should this powerful but demanding gaze turn next? The ultimate test for this cosmic key may lie not beneath a city, but within a silent, unopened hill in central China. This is the Mausoleum of the first Qin Emperor, a burial complex so vast and legendary it challenges the very limits of non-invasive exploration. Above ground, the world knows the breathtaking ranks of the terracotta army, thousands of life-sized clay soldiers standing in perpetual guard. Yet their true purpose was to protect the emperor's final resting place, a colossal earthen mound rising from the landscape, its interior sealed for over 2,000 years. Ancient texts describe a subterranean palace with ceilings inlaid with pearls to mimic the night sky, and vast-scale models of rivers and seas flowing with liquid mercury. These accounts, while poetic, present a modern dilemma of immense scale and sensitivity. The mound itself is a man-made mountain, far larger than the Great Pyramid at Giza in volume. Its core is a labyrinth of packed earth, timber, and stone, and potentially, according to historical records, hazardous materials that make traditional excavation not just difficult, but dangerously irresponsible. How then do we respectfully seek to understand what this monumental structure contains without ever breaking its seal? This is where muon imaging proposes a revolutionary, ethical path forward. Researchers from Japan have outlined a bold theoretical plan to scan the mound from a distance. Instead of placing detectors inside the tomb, which is impossible, they would position them in tunnels dug into the bedrock far beneath the mound's base. From this vantage point, the entire mass of the burial structure would rise above them, acting as a natural filter for the cosmic rain. The detectors would patiently count muons passing downward through hundreds of feet of earth and architecture, slowly building a density map of the entire interior. The technical challenges are staggering. The mound's sheer size means a survey would require an unprecedented number of detectors and years of data collection to achieve a clear image. Differentiating between a packed earth wall, a timber chamber, a stone corridor, and the potential signature of dense liquid mercury would require incredibly precise calibration and analysis. Yet the potential reward is a glimpse into one of history's most iconic sealed spaces. A successful Muon map would not provide a treasure inventory, but an architectural blueprint. It could reveal the layout of major chambers, the presence of large structural voids, and perhaps even hint at the flow of major features described in the ancient texts. This information would be priceless for cultural preservation. It would allow scholars to understand the mound's structural integrity, to monitor it for any unseen shifts or voids that could threaten its stability, and to make informed, century-spanning decisions about its stewardship. Most importantly, it would do all this through a completely passive, external observation. The tomb would remain inviolate, its peace undisturbed, while still sharing profound secrets about the ambition of the emperor who first unified China. This proposal represents the highest aspiration of the technology, a promise to satisfy our deepest curiosity about the past through a method that honors and protects the past itself. The silent data collected within the pyramid is a language of numbers, not images. After months of listening, researchers emerge not with a photograph, but with colossal digital ledgers containing millions of particle trajectories, each one a single data point in a cosmic pointillist painting. The transformation of this raw numerical torrent into a three-dimensional map is a feat of modern digital alchemy, happening not in the desert, but in the hum of supercomputing clusters around the world. The core technique is called Muon Tomography, and it shares a fundamental principle with the medical CT scans used in hospitals. In a CT scan, an X-ray machine rotates around a patient, taking many two-dimensional images from different angles. A computer then uses a sophisticated mathematical algorithm to reconstruct those flat slices into a complete three-dimensional model of the body's interior. Muon tomography works in a similar way, but instead of a rotating machine generating the signals, the rotation is provided by nature itself. Muons rain down from all angles across the sky. The detectors, fixed in one place inside the monument, record the direction and number of particles arriving from every point in the hemisphere above them. It is as if the sky itself is the rotating scanner, and the pyramid is the patient. The algorithm's job is to take all those millions of angled paths and calculate, backwards, what arrangement of dense stone and empty space would have allowed that specific pattern of particles to get through. This computational challenge is immense. The algorithm must account for the natural background rate of muons, the energy they lose as they pass through material, and the statistical noise inherent in any random natural process. A key question throughout is one of significance. Is a cluster of extra muons coming from one direction a real sign of a void, or is it just a random fluctuation, like flipping a coin and getting 5 heads in a row by chance? Scientists use powerful statistical tests to calculate confidence levels. They might say a detected anomaly has a 5 sigma confidence level, which in simpler terms means the probability of it being a random fluke is less than 1 in 3.5 million. It is this rigorous statistical gatekeeping that turns an intriguing maybe into a publishable discovery. Once the data passes these tests, the final step is visualization. Using the same software that creates special effects for films or models complex engineering projects, data scientists assign colors and transparencies to different density values. Solid rock might become a translucent amber, while the big void glows a bright, solid blue. The result is a navigable three-dimensional model, a ghostly digital twin of the monument's hidden heart. An archaeologist can put on a virtual reality headset and literally fly through the solid stone, examining the size, shape, and orientation of a void from angles no human could ever physically achieve. This is more than a pretty picture, it is a powerful hypothesis generator. Seeing the void in 3 dimensions might suggest its structural purpose or how it relates to known passages. It allows for precise measurements and the planning of future, minimally invasive verification. This behind-the-scenes digital archaeology lab, where physics, statistics, and computer art converge, is where the whispers of cosmic particles finally become a story we can see and explore. It turns abstract probability into a shared experience of discovery. The glowing digital models and confirmed voids tell only part of the story. For every clear discovery, there are countless hours of patient listening that yield only silence or ambiguous whispers that resist easy interpretation. This is the crucial, grounding reality of muon imaging, a technology of immense power defined by equally significant boundaries. Its resolution is measured in meters, not centimeters. This means it can reveal a chamber the size of a bus, but it will likely miss a small collection of ceremonial objects or a single sealed sarcophagus tucked within that space. The technique relies on a stark contrast in density, the dramatic difference between solid stone and empty air. If a hidden space were filled over centuries with silt, water, or collapsed rubble, its signature could blend into the surrounding material, becoming invisible to the cosmic rain. And the process demands immense patience. Building a statistically significant image requires detectors to listen for months, sometimes over a year, a timeline dictated by the random, gentle drizzle of particles from the sky. This inherent slowness means it cannot provide quick answers to urgent archaeological questions. These limitations are not failures, but the defining parameters of the tool. They teach us what kind of secrets the stone is willing to give up and which ones it still guards closely. Consider the many scans within other pyramids at Giza and elsewhere that have not revealed major new chambers. These non-discoveries are scientifically vital. They tell us that certain structures may indeed be more solidly packed than we theorized, or that their builders did not incorporate the same kind of relieving architecture. An empty result is still a result, one that helps refine our historical models and directs precious resources toward more promising targets. This honest accounting of boundaries is essential, not to diminish the technology's wonder, but to frame its true revolutionary potential. It charts the course for the next generation of detectors. Researchers are already working on systems with finer granularity, using more sensitive materials and advanced algorithms to tease out fainter signals. The future may bring portable detectors that can be deployed faster, or networks of them that can gather data more efficiently. By understanding where the walls are today, we can see the doors they will open tomorrow. The cosmic key is still being forged, each limitation a guide for its next, more precise shaping. The true scope of this technology extends far beyond the pyramids and volcanoes we have already explored. If we allow our imagination to follow the path of these particles, we can envision a future where the hidden anatomy of our entire built heritage comes into view. Consider the soaring stone vaults of a great medieval cathedral like Notre Dame in Paris. Following its restoration, muon detectors could be placed within its nave and crypt not to find new chambers, but to create a permanent, three-dimensional blueprint of its structural bones. They could map the precise layout of hidden buttresses, the distribution of stress within ancient pillars, and locate any voids or weaknesses left by time, fire, or water. This would not be a single discovery, but a living health scan for a monument, a tool for conservators to predict and prevent future decay with unparalleled precision. Now, shift the scene to a windswept coastal fortress, its stone walls scarred by centuries of conflict. Historians have long wondered about the network of siege tunnels reportedly dug beneath its foundations during a famous siege. Traditional excavation might be impossible without risking the collapse of the historic walls above. But a muon scan from within the fortress's dungeons or from tunnels in the bedrock below could reveal those very hollows, tracing the ghostly paths of miners and counterminers through the earth, turning legend into mapped reality. The same principle could probe the fortress walls themselves, searching for concealed priest holes, forgotten armories, or sealed oubliettes, architectural secrets meant to stay hidden. Even sites we believe are fully understood could yield new layers. Take a place like Pompeii, meticulously excavated for centuries. Muon imaging could peer beneath the excavated streets and villas, revealing undisturbed lower levels, earlier iterations of the city, or the vast, unmapped network of water channels and storage cellars that supported Roman life. It offers a way to excavate downward without moving a single shovelful of volcanic ash. Then there are the great enigmatic mounds like Silbury Hill in England, an artificial chalk hill built over generations in the Neolithic period. Its purpose remains one of archaeology's great puzzles. A muon scan from within a tunnel at its base could finally reveal if its core holds a ceremonial chamber, a labyrinth of ritual passages, or if its meaning is contained entirely in the act of its colossal construction. These are not mere fantasies, but logical extensions of a proven principle. Each theoretical application highlights how muon imaging could democratize discovery. It is not a tool solely for the most famous or funded sites, but a potential key for local historians studying a regional castle, for indigenous communities seeking to understand ancestral earthworks without disturbance, or for teams working to stabilize ancient temples in jungles and deserts worldwide. The cosmic rain falls equally on all. By learning to interpret its shadows, we gain the potential to listen to the hidden stories within every culture's monumental legacy, asking new questions of places we thought had given all their answers, and discovering that the greatest chapters of our shared history may still be waiting silently in the stone. Beneath the bustling streets of modern Istanbul, a hidden city of water sleeps in darkness. This is not a myth, but a monumental feat of engineering, a network of vast underground cisterns built by Byzantine emperors to sustain a metropolis. The most famous of these is the Basilica Cistern, a breathtaking subterranean palace of 336 marble columns, where visitors today walk on platforms over dark, still waters. But this grand chamber is just one known node in a sprawling hydraulic web. For years, archaeologists have suspected it connects to other lost cisterns and passageways, veins of a forgotten infrastructure that once pulsed beneath the ancient city. To find these links without drilling through centuries of urban layers, a team of Turkish and Japanese researchers turned to the cosmic rain. Their mission was a masterclass in adapting muon imaging to one of its most complex environments yet, a publicly accessible, humid tourist site. The logistical challenges were immediate and profound. Unlike a sealed pyramid, the Basilica Cistern is alive with humidity from its reservoir and the breath of thousands of daily visitors. Muon detectors are precise electronic instruments, and moisture is their enemy. the team had to design and build custom, hermetically sealed housings for their equipment, creating little technological islands within the damp, historic space. They worked during off hours, carefully installing their arrays amidst the forest of columns, ensuring not a single cable or bracket marred the ancient stone. Every step required a delicate balance between scientific rigor and the paramount need to preserve both the site and the visitor experience. The core question was one of urban anatomy. Did the known walls of the Cistern hide arched portals leading to adjacent chambers? Could muons trace the ghostly outline of bricked-up aqueduct channels that once fed this reservoir from distant forests? By placing detectors at strategic points within the accessible space, the team aimed to peer into the earth in every direction, not just upward. They were searching for the signature of other voids, mapping the density of the surrounding soil and masonry to distinguish natural geology from human-made emptiness. This study exemplifies a powerful shift in scale and purpose for muography. Here, the goal is not a single hidden tomb, but the revelation of a system. It is urban archaeology at its most essential, seeking to understand the literal foundations of a megacity, the hidden machinery that allowed Constantinople and later Istanbul to thrive. The data from such a scan does more than satisfy historical curiosity. It provides a critical safety map for the modern city built atop it. Knowing the precise location and size of these subterranean cavities is vital for contemporary construction projects, tunnel drilling, and conservation efforts. A new subway line or a building's foundation must navigate this hidden landscape, and a collapse into an unknown cistern could be catastrophic. By providing a non-invasive blueprint, muon imaging helps protect both the priceless heritage below and the vibrant city above. It transforms the cistern from a static museum piece into a living part of the city's structural understanding, a bridge between the ingenious hydrological mind of the Byzantine engineer and the modern urban planner. The silent particles passing through the humid air and ancient brick become consultants in preservation, ensuring that the hidden wonders of the past continue to safely support the future. This cosmic conversation between disciplines did not happen overnight. The success of muon imaging hinges on a partnership between two worlds that have long operated in separate spheres. On one side, particle physicists, thinkers fluent in the language of quantum mechanics and statistical probability. On the other, archaeologists and historians, interpreters of cultural context and material traces. Their collaboration is a human story of learning to listen, and it is as groundbreaking as the discoveries it enables. For a physicist, a pyramid is a mass of limestone, a density profile waiting to be decoded. Their primary concern is signal-to-noise ratios, detector placement, and achieving a 5 sigma confidence level. An archaeologist, however, sees a pyramid as a cultural text, a product of specific religious beliefs, royal authority, and construction logistics. When the physicist presents a grainy muon map showing an anomaly, the archaeologist's first question is not about statistical significance, but about intent. Could this shape be a chamber? Would its location make sense for a relieving space or a ritual purpose given what we know of 4th dynasty engineering? The physicist must learn to ask these questions, to understand that not every density variation is a room. It could be a construction gap or a later fissure. They must grasp that the most exciting scientific signal might be archaeologically meaningless, and the faintest whisper could be a historical revelation. Conversely, the archaeologist must step into the physicist's world of uncertainty. Dr. Mehdi Taoubai, a co-founder of the ScanPyramids mission, often speaks of this translation. An archaeologist wants a definitive answer, a clear wall on a map, but a physicist can only provide a probability, a shadow with confidence intervals. The archaeologist learns to think in terms of likelihoods, to weigh evidence not as proof, but as a compelling guide for the next hypothesis. they come to appreciate the immense effort behind each data point, the years of work condensed into a single, glowing patch on a screen. This mutual education builds a new, shared vocabulary. Terms like void and anomaly take on layered meanings, bridging the gap between particle tracks and pharaonic blueprints. The magic, the true eureka moments, happen when these two languages suddenly align. Professor Kunihiro Morishima, whose team found the big void, describes the electrifying instant when the Muon data revealed a void with a shape and scale that mirrored the grand gallery below. The physicist saw a statistically robust density contrast. The Egyptologist saw an architectural parallel that screamed intentional design. In that convergence, a raw data point transformed into a chapter of human history. It was not just a hole in the rock, it was a clue to the ancient mind. These moments of shared discovery forge a profound respect. The physicist gains awe for the cultural puzzles of the past, and the archaeologist gains a deep appreciation for the rigorous, patient logic of fundamental science. This cross-cultural collaboration within science is itself a monumental achievement. It builds bridges of knowledge as sturdy as the stone they investigate, proving that the greatest secrets are unlocked not by a single field of expertise, but by the combined gaze of many. It raises a compelling question for our future. What other hidden dialogues between disciplines are waiting to be started? And what ancient mysteries might they solve together when we finally learn to speak each other's languages? That cross-cultural dialogue extends beyond the lab and into the living rooms of millions. The true power of a discovery lies not just in the data, but in its ability to ignite wonder, to transform complex science into a shared story of human curiosity. Projects like ScanPyramids have mastered this art of translation, turning the invisible process of muon imaging into a visible, global spectacle. They understand that the journey of discovery is as compelling as the destination. Through breathtaking documentaries, we are invited into the cramped chambers alongside the scientists, feeling the palpable tension as data loads and the first ghostly images take shape. Interactive websites allow anyone to explore three-dimensional models of the voids, toggling between the solid exterior and the transparent interior, making the abstract concept of a density map feel tangible and personal. Museums worldwide have created immersive exhibitions where visitors can walk beneath a model of the pyramid, watching simulated muons streak through the stone to reveal hidden spaces in real time. This is science communication at its most effective, leveraging the primal wow factor of seeing inside a sealed tomb. That single, powerful image serves as an irresistible gateway. A person drawn in by the mystery of the pyramid suddenly finds themselves learning about cosmic rays, not from a dry textbook, but as the essential messengers that made the discovery possible. They are introduced to particle physics through the story of the muon, a fundamental piece of the universe passing through them right now. The entire painstaking methodology, the years of detector placement, the statistical analysis, becomes a masterclass in the scientific method, a real-world demonstration of how patience, collaboration, and rigorous testing lead to new knowledge. This public engagement is not a secondary benefit, it is a vital pillar of the work. By making the science visible and exciting, these projects build a broad base of support, translating public fascination into sustained funding and institutional backing for future expeditions. More importantly, they plant seeds of inspiration. A child watching a documentary about finding a hidden void might not just dream of being an archaeologist, but of being the physicist who builds the detector, the engineer who solves the power problem in the tomb, or the data scientist who writes the algorithm to see the unseen. The ancient mystery becomes a catalyst, transforming passive viewers into active learners and potential future explorers. It proves that the most profound scientific journeys can begin with a single, simple question anyone can ask: what secrets are hidden inside that mountain of stone, and how can we find them without ever touching a single block? The tools of cosmic vision are themselves evolving at a breathtaking pace. What once required a truckload of delicate equipment and a dedicated power grid is now shrinking towards the realm of the practical and portable. The next wave of muon imaging is being forged from new materials, particularly advanced plastics. These plastic scintillators are not just lighter and more robust than their crystal predecessors, they are also far less expensive to produce. Imagine a detector array that can be packed into a few rugged cases, transported by a single vehicle, and set up by a small field team in a matter of days rather than months. This leap toward portability is the key to democratizing the technology. It promises a future where a research team studying a remote Maya pyramid complex or a medieval castle in the highlands could conduct a preliminary muon survey as a standard part of their initial assessment, just as they now use ground-penetrating radar. The barrier to entry, once measured in millions of dollars and years of planning, could soon be within reach of university departments and heritage organizations worldwide. But the revolution is not only in the hardware collecting the data, it is in the mind interpreting it. The torrent of information from these detectors is a perfect challenge for artificial intelligence. Machine learning algorithms trained on vast simulated datasets and real-world results from past scans are learning to see patterns human analysts might miss. They can filter out statistical noise with incredible efficiency, identify faint, complex shapes within the density maps, and even begin to classify anomalies. An AI might cross-reference the subtle signature of a potential void with architectural data from similar sites, suggesting with high probability whether it resembles a known type of burial niche, a construction corridor, or a natural fissure. This intelligent analysis could compress years of data processing into weeks or even days, accelerating the cycle of discovery from a patient listening into a dynamic conversation with the past. The cosmic whispers will be heard and understood faster than ever before. The final frontier is clarity itself, spatial resolution. Current muon maps are brilliant for revealing large chambers, but their pixelated nature can obscure finer details. The quest now is to sharpen that cosmic lens. Researchers are experimenting with novel detector geometries, arranging scintillating fibers or gas tubes in dense, three-dimensional grids to track particle paths with micrometer precision. Other teams are pioneering hybrid techniques, combining muon data in real time with inputs from sonar, radar, or even gravity sensors. By fusing these different senses, a composite image emerges with stunning definition, potentially revealing not just the outline of a room, but the texture of its walls or the presence of large internal features. We are moving from seeing shadowy blobs to reading the architectural handwriting within the stone. Envision an archaeologist of the next decade arriving at a newly discovered earthen mound. Alongside their traditional tools, they unpack a series of modular detector units, linking them together like high-tech Lego blocks around the base of the structure. Within a week, the system has gathered enough data for an on-site AI to process, generating a preliminary three-dimensional density model on a tablet screen. The team can immediately see the likely location of major voids and make informed decisions about where to focus their conservation efforts or plan a minimally invasive endoscopic camera probe. This is not science fiction, but the logical trajectory of a field leaping forward. When muon imaging becomes as routine as aerial photography, the very landscape of archaeology will transform. We will no longer be limited to probing a handful of iconic sites per generation, but will be empowered to listen to the hidden stories within thousands of forgotten monuments, turning the silent rain into a global conversation with history. South of Egypt, along the banks of the Nile, stand monuments to a rival power that once conquered the pharaohs themselves. These are the Pyramids of Meroë in modern Sudan, the legacy of the Kingdom of Kush. Sharper and steeper than the iconic shapes at Giza, These Nubian pyramids crown the tombs of kings and queens who ruled a vast, wealthy empire for centuries. While their silhouettes are familiar, their internal stories have been brutally fragmented by centuries of looting. Treasure hunters from ancient times to the modern era have tunneled into their cores, seeking gold and leaving behind hollowed-out, confusing labyrinths. For archaeologists, this presents a profound puzzle. With the original chambers so thoroughly disturbed, how can we ever understand the true layout of these tombs, the sequence of rooms, or the burial practices they were built to contain? Traditional excavation here often feels like reassembling a shattered vase after someone has already taken all the pieces. This is where Muon imaging proposes a different path, one of respectful reconstruction rather than invasive recovery. By placing detectors around these damaged structures, researchers could peer through the stone to map the density of everything inside. The goal would not be to find a single hidden void, but to untangle the entire architectural blueprint from the chaos of later intrusions. The scan would distinguish the solid, original walls from the ragged tunnels cut by looters. It could reveal the ghostly outline of a sealed burial chamber that might have been missed, or trace the path of a descending corridor now filled with rubble. Each pyramid at Meroë has a distinct profile, and their internal designs evolved over time, reflecting changes in royal ritual and belief. A Muon map could chart this evolution non-invasively, showing how chamber shapes shifted, or how architects might have incorporated hidden niches for offerings. This application shifts the technology's role from discovery to forensic archaeology. It becomes a tool for healing our understanding, allowing us to see the monument as it was intended, not as it was violated. For a site like Meroë, which has far fewer resources for large-scale, destructive excavation than more famous locations, this passive, powerful scanning offers a form of democratization. It provides a world-class diagnostic tool to a World Heritage Site that deserves deep study, enabling local and international teams to plan precise, conservation-focused interventions that protect what remains. The cosmic particles falling equally on the pyramids of Giza and Meroë do not distinguish between famous and overlooked. They offer the same clarity to all, promising to illuminate the sophisticated heart of Kushite culture and restore dignity to the architectural legacy of a civilization that once ruled the Nile. A confirmed void within a pyramid is not merely a discovery, it is a profound responsibility. The moment the Muon map resolves into a clear, undeniable shape, a new and difficult question emerges for every scientist and historian involved. Do we now attempt to enter that space, or do we leave it sealed? This is the ethical frontier where the thrill of knowledge meets the solemn duty of preservation, and there is no simple answer. The impulse to excavate is powerful, driven by a fundamental human curiosity to see, to touch, and to finally understand what has been hidden for millennia. The potential rewards are immense, a glimpse into untouched ritual, unprecedented artifacts, or a complete rewriting of a historical narrative. Yet this impulse must be weighed against very real and permanent risks. The very act of opening a sealed environment that has been in perfect equilibrium for thousands of years can trigger its rapid decay. A sudden influx of modern air, with its humidity, pollutants, and microorganisms, can cause fragile pigments to fade, organic materials like wood or textiles to crumble to dust, and stable metals to begin corroding. The environmental control of a 4,500-year-old chamber is delicate and unknowable. Furthermore, the structural integrity of the monument itself could be compromised. Drilling a small borehole to insert a camera might seem minor, but it could alter stress distributions in the ancient masonry or introduce vibrations that destabilize adjacent chambers. An excavation, even a careful one, is an irreversible intervention. Once you open the door, you can never truly close it again. This leads to a guiding principle gaining prominence in modern archaeology: stewardship over ownership. The idea is that we are not the owners of these sites, but their temporary caretakers. Our primary role is not to extract everything we can for our own generation's museums and academic papers, but to preserve the full integrity of the site for future generations who will have tools, techniques, and perspectives we cannot yet imagine. What if 50 or 100 years from now, a technology exists that can analyze the contents of a sealed chamber in perfect detail without ever breaching a wall? By excavating today with our comparatively crude methods, we might forever destroy that future possibility. We might gain answers to our current questions, but in doing so, we could obliterate the evidence needed to answer the deeper questions our descendants will ask. Muography, therefore, does more than reveal hidden spaces. It fundamentally reframes our relationship with them. It gives us the incredible gift of knowing something is there, while simultaneously presenting the choice to let it remain. This technology forces a more mature, patient conversation about the past. It asks us to consider that sometimes the greatest act of respect for history is not to possess it, but to protect its mystery, to listen to its silence, and to ensure that its untold stories remain intact for the listeners of tomorrow. This shift in perspective is quietly revolutionizing the entire practice of archaeology itself. For centuries, the discipline has followed a fundamental rhythm. A scholar forms a hypothesis based on surface surveys or historical texts, and then the team begins to dig, testing that idea through the physical removal of soil and stone. It is a powerful but inherently destructive process, where the context of an artifact is often altered the moment it is lifted from the ground. Muon imaging introduces a radical new step into this rhythm, a phase of comprehensive, non-destructive pre-mapping. Imagine an archaeologist approaching a mysterious mound not with a shovel, but with a cosmic scanner. Before a single trowel touches the earth, they can now possess a three-dimensional blueprint of the entire internal structure. This transforms the entire endeavor from a deductive guess into an informed conversation with the site. Excavation, when it does proceed, is no longer a broad search. It becomes a targeted, surgical procedure. Knowing the precise location and dimensions of a potential chamber allows conservators to plan the safest possible access route, to anticipate structural weaknesses, and to prepare the perfect environmental controls to protect whatever might be inside the moment it is exposed to modern air. The very goal of excavation changes. It is no longer about finding out what is there, but about carefully confirming and documenting what you already know is there. In some cases, this map may even suggest that excavation is not the best path at all. For extremely fragile or culturally sensitive sites, the Muon data itself can become the final record. Researchers can conduct a complete virtual excavation, using the density map to study the architecture, theorize about function, and even create immersive public experiences that allow anyone to explore the hidden chambers without ever disturbing a grain of sand. This represents a leap toward a more humble and sophisticated stewardship. We are learning that understanding does not always require possession, and that the deepest respect for the past can sometimes mean preserving its secrets intact while still marveling at their shape and scale. This integration of particle physics into the mud and trowel world of archaeology is part of a broader, exciting trend. The field is embracing big science, weaving together tools from engineering, advanced computing, and data analytics to ask questions that were once impossible. It allows us to protect our shared cultural heritage with the same level of technological sophistication we use to build our futures. The silent reign of muons is not just revealing hidden rooms, it is drawing a new blueprint for discovery itself, one where our first instinct is to listen patiently to the story the stone is willing to tell before we ever decide to turn the page. The ancient heart of Rome is a layered text, written and rewritten in brick, tufa, and concrete over 2,500 years. beneath the modern traffic and bustling piazzas, foundational walls from the Republic and Empire still stand, often incorporated into later buildings or simply buried by the rising ground level of the city. One of the oldest and most enigmatic of these structures is the Servian Wall, a massive defensive barrier built in the 4th century before the Common Era to protect the early city. Sections of it still emerge like geological strata from the basements of modern buildings or along railway cuttings. Historians have long studied its surviving stretches, but its full construction sequence and relationship to other lost monuments remain partly shrouded. Ancient texts describe grand public porticos, covered walkways that were centers of social and political life that were built adjacent to or incorporated parts of this wall. Yet their precise footprints have vanished from the surface map of the city. This is where Muon imaging proposes a new kind of urban archaeology. Researchers have outlined plans to place detectors in the underground spaces that already exist near these ancient walls, in subway station service tunnels, museum basements, or archaeological crypts. From these vantage points, the cosmic rain would pass sideways through the monumental masonry. The goal is not necessarily to find a single hidden chamber, but to read the wall itself as a historical document. A muon density map could reveal internal cavities, perhaps the remains of blocked-up gateways or staircases within the wall's thickness. It could distinguish between different construction phases, showing where repairs were made with different materials after a siege, or where a later emperor's builders attached a new structure. Most tantalizingly, by scanning laterally from within the Servian wall, the particles might detect the faint, parallel signature of a dense foundation trench or avoid just beyond it the ghostly imprint of a lost portico's colonnade foundation, buried under centuries of urban buildup. This application shifts the scale and context of discovery dramatically. The challenge here is the modern city itself. Unlike the controlled, isolated environment of a desert pyramid, Rome is a living, vibrating organism. Installing sensitive muon detectors means negotiating access to secure underground infrastructure, shielding equipment from ambient electromagnetic noise, and accounting for the constant, subtle vibrations from traffic and subways that could affect long-term measurements. The detectors must operate unseen and undisturbed in service corridors, perhaps for over a year, to gather enough data from the dense stone. Yet the potential reward is a new clarity on urban evolution. By mapping the density variations within and around these foundational walls, Muography could help trace how the city's ceremonial and defensive spaces transformed from the Republican era through the Imperial Age. It turns the wall from a static, surface ruin into a dynamic, three-dimensional core sample of Rome's growth. Each variation in density becomes a sentence in the story of the city's resilience, telling of repairs after an attack, of architectural fashion changing, or of a grand public space that faded from memory but left its structural shadow in the earth. This case study redefines what we consider a monumental structure. It is not just a pyramid or a temple, but the very grid of the ancient city, its skeletal walls still holding the shape of a lost world. If successful, such a scan would demonstrate that the cosmic key can unlock history not only from sealed tombs, but from the foundational stitches that hold the fabric of an ancient metropolis together. The romance of discovery has never truly been about the treasure at the end, but about the quest itself. For generations, that quest was personified by the lone adventurer, the figure like Indiana Jones, braving physical danger to pull a priceless artifact from the dust. Yet the modern explorer looks different. They are just as likely to be found in a clean room calibrating a scintillator as in a desert trench, their machete replaced by a laptop running complex algorithms. Muon imaging represents the beautiful fusion of these two archetypes. blending the romantic allure of uncovering lost worlds with the meticulous rigor of a particle physics laboratory. It proves that the heart of adventure still beats powerfully, but its pulse is now measured in data points and confidence intervals. This is a new kind of hero's journey, one where the labyrinth is made of statistics, and the Minotaur is the tantalizing ghost of a statistical anomaly. The thrill of seeing that first shadow of the big void on a screen was not so different from the thrill of brushing sand from a forgotten inscription. Both are moments where the unknown reluctantly yields a secret. This technology demonstrates more clearly than ever that the grandest mysteries of our time are no longer hidden in unmapped jungles, but in the uncharted intersections between fields of knowledge. The most compelling stories are being written by teams where a historian's intuition about ancient ritual meets a physicist's understanding of cosmic rays, where an engineer's solution for powering a detector in a pyramid becomes as critical to the plot as deciphering a cryptic map. It creates a powerful, modern narrative for discovery, one that is collaborative, interdisciplinary, and driven by a shared curiosity rather than solitary conquest. This narrative holds a special power to inspire. A child captivated by the idea of a hidden chamber in the Great Pyramid might not just dream of wielding a whip and fedora, but of designing the sensor that made the discovery possible. They might see themselves as the programmer who writes the code to visualize the void, or the project manager who coordinates an international team across continents and languages. Muon imaging makes the tools of fundamental science tangible and heroic, tying the abstract beauty of a subatomic particle directly to the concrete wonder of a 4,000-year-old monument. It shows that you do not have to choose between the romance of history and the precision of science. You can live in the exhilarating space where they meet. This is the ultimate promise of such work. It reassures us that the age of discovery is far from over. The maps are not all filled in, they have simply changed form. The blank spaces now exist within the stones of our greatest monuments and in the gaps between our scientific disciplines. The call to adventure is still being issued not by a dusty parchment, but by a subtle excess of muons counted in a detector, a whisper from the cosmos that says, "Look closer," for the greatest stories are still waiting patiently to be read in the language of the universe itself. The story of muon imaging is ultimately a story of connection. It threads together the unimaginable violence of distant supernova with the quiet ambition of a pharaoh's architect. It links the sterile precision of a particle physics lab with the humid, dusty air of a 4,000-year-old chamber. This technology has shown us that the universe is not a separate spectacle, but a participant in our own history, its most fundamental particles acting as silent scribes, recording the density of our greatest monuments in a language we are only now learning to translate. Our journey through the science, from cosmic rays to scintillator flashes, has revealed not just a tool, but a new way of seeing. We have watched it confirm long-held theories about structural chambers in Giza, while dismantling the hope for others, proving that its power lies in truth, not just in spectacle. Each case study, from the pyramids to the volcanoes, from the cisterns of Istanbul to the mounds of Meroë, has deepened a central wonder, the realization that so much of our past is not lost, but simply unseen, waiting for the right kind of light. The voids it maps are far more than empty spaces in stone. They are physical questions carved by ancient hands. Is this a chamber for a king, or a beam to support a ceiling? Is this a natural fissure, or a path dug by a desperate miner during a siege? Each shadow on the Muon map is an invitation, a starting point for a new conversation between the present and the past. As the detectors shrink in size and grow in sensitivity, as artificial intelligence learns to interpret their whispers with greater clarity, and as collaborations between physicists and archaeologists become the standard and not the exception, we are not ending an exploration, we are stepping across its threshold. This is the beginning of a quieter, more profound kind of discovery, one guided by listening rather than taking. We now have a key that can respect the sanctity of a sealed tomb while still learning its story. So we leave you with this thought: the cosmic rain continues to fall, and every monument on Earth is being scanned right now by particles from the stars. The only thing left to decide is where we will place our detectors and which silent story we will choose to hear next. If this fusion of cosmic scale and human history resonated with you, there are more mysteries waiting to be unraveled. Subscribe to continue this journey of discovery, and let us know in the comments below if you could point a muon detector at any one structure in the world, ancient or modern. Which would it be, and what do you hope we might find?